Hi, welcome to Team 16's chemical engineering presentation on our project to turn natural gas into methanol. Our team consists of Emily Steigerwald, Mary Miller, myself, Lucas French, and Timothy Roehm. Our company, Knitline Chemicals, has 3 locations across the United States. Our first is in Houston, Texas. Our second is in State College, Pennsylvania. This is our research division where Team 16 actually planned the development for our second chemical plant in Philadelphia, Pennsylvania. Our reason for choosing Philadelphia was because we already had facilities there in place, so it wouldn't need to be a grassroots plant, and we were also in proximity to the Marcellus Shale, so that we could get cheap and affordable natural gas. So our goal, again, was to take natural gas and turn it into methanol. We purchased the natural gas at 4.3 cents per pound and turned it into a purity of at least 99.85% so that we could sell it at 12.5 cents per pound. So our plant took the rate of natural gas at 45,300 pounds per hour and turned it into 71,000 pounds per hour methanol. This gave us a final purity of 99.97% methanol, and this definitely meets our spec of 99.85%. And this gives us an overall conversion of 99.6% mole methane conversion.
In this presentation, we're going to cover 3 main points. We're going to start by talking about the design methodology that we followed when we were designing our process. Next, we're going to cover an economic evaluation of the entire process. Finally, we're going to talk about some specifications that our process needed to meet to be viable. First, I want to walk you through the block flow diagram of our process. We start here in stage 1 with purification of the natural gas raw material. You can see we start with a mercury adsorption column, followed by a hydrogen sulfide adsorption column. These 2 are the most dangerous contaminants, as they can either poison the catalyst or corrode some of the process units downstream. So we want to get rid of them first. Going to stage 2, we have our steam reformer, where you turn our natural gas feed into syngas. As you can see, prior to the steam reformer, we're adding steam to our process, which increases our hydrogen to carbon ratio to prevent coking in the downstream process units. In stage 3, we have our methanol synthesis reactor, where we turn our syngas into our methanol. The conversion in the methanol synthesis reactor is rather low, so we used a knockout drum followed by a recycle stream to recycle the unreacted reactants back into the methanol synthesis reactor to up our product production. Moving on to stage 4, we have another purification step where we have 2 distillation columns, the first of which removes methyl formate from the system, and the second of which removes ethanol and water and leaves us with our product stream of methanol. I also want to discuss the outside battery limits of our process. The outside battery limits include storage tanks and a steam boiler, which produces the steam used in our heat exchangers. Heat exchangers in phase 2 and phase 4 of our process use high, medium, and low pressure steam to heat and cool our process stream. As you can see, there's a steam boiler which produces high pressure steam, which is then lowered to the desired pressures of steam that are then used in our phases. The condensed vapor coming out of these heat exchangers is then recycled to the steam boiler to be used again in the process.
Next, we will be talking about the steam reformer, which converts our natural gas stream into syngas, which contains hydrogen gas, carbon monoxide, and carbon dioxide. It is running at 290 psi and 1750 degrees Fahrenheit, which is very high and will require a lot of energy from our fire heater, which will be providing a duty of 149.3 million BTUs per hour. Now, this is a tube and shell reactor, and the stream coming from this will be then going to the methanol reformer. The methanol synthesis reactor is designed to use Fischer-Tropsch reactions to convert the syngas into methanol. It is running at 1015 psi, which is very high, but required to bring the reaction to completion, and almost 500 degrees Fahrenheit. This is a slightly exothermic reaction, meaning that we will need to use oil to cool the reactor 2.2 million BTUs per hour. This will then move to the first distillation column, which is a partial condenser, and that will be running at 15 psi and 100 degrees Fahrenheit. The purpose of the first column is to remove some of the methyl formate and more volatile gases such as carbon dioxide out of the distillate, while the bottoms will go on to the second distillation column running at 15 psi and 150 degrees Fahrenheit. The purpose of the second column is to now remove ethanol and provide our product. Next, we'll be talking about the PDRI, or Project Rating Definition Index, which discusses the definition of our project throughout all of the gates. You can see with the first gate, or third gate, first rating index, we're between the bounds of typical minimums and maximums, and as the project progressed, definition did increase, but it was outside of typical bounds. This is because our project scope did not include such things as building and construction elements or permits and things of the like, as they were outside of the scope of the project. Throughout the project, we did increase definition very steadily, and that's what the PDRI shows.
To determine the feasibility of our process, an economic evaluation was performed. This evaluation included capital costs, operations costs, and associated fixed costs. The capital cost of the process equipment were estimated for each stage of the process. In stage 1, the major contributor to the capital cost here was the sulfur adsorption unit. There was a large amount of sulfur coming in with the natural gas feed. Therefore, a large volume of sulfur adsorbent, also large volume of reactor, is required to remove the sulfur from the natural gas. In stage 2, the main contributor to the capital cost is the steam reformer. Due to the steam reformer operating at very high temperatures, special alloys such as Hastelloy or Inconel is required for this reactor, as well as the heat exchanger directly before the reactor. These alloys are very expensive, therefore drive up our capital cost. Finally, in stage 3, the main contributor to the capital here are the compressors, which are required to pressurize the process stream to the required pressure for the methanol synthesis reactor. In total, the process equipment is estimated to cost approximately $132 million. In addition, capital costs are associated with developing and expanding the current facilities of the site. These factors include expanding on the utilities available, as well as product storage and other site developments. Overall, this is going to add to the capital approximately $256 million. In addition, total capital costs also include other associated costs that are scaled based to the contractor costs that we have discussed previously. These include administrative, startup, initial catalyst and adsorption loading, and other miscellaneous costs. Overall, all of the capital cost is estimated to cost $472 million. We also looked at our operating costs. Overall, the operating costs are estimated to cost $120 million annually. Please note that although the waste here is shown as a 0%, this does have a value. Just respective to the raw materials and utilities, it is much smaller. The raw material costs include the natural gas feed, which is approximately $16 million annually. Other costs that come into the raw materials are the process water and the continued loading of adsorbents and catalyst. Overall, the cost of raw materials contributes approximately $45 million annually. Utilities were also of concern. Overall, they are estimated to cost $41 million annually. The largest contributor to this is the power required to operate the compressors and pumps required for the process. Another contribution here is given by the propane refrigerant, which is used in heat exchangers to cool the process stream. Additional fixed costs are also associated with the operation of the plant. This includes things such as labor, repair and maintenance, property tax, and insurances. Overall, this contributes approximately $42 million annually. Taking all of the capital, operation, and fixed costs of the process into account, we determined that the process will not be economical. The price of methanol is currently approximately 12.5 cents per pound. However, taking all of our costs into account, the total cash cost of running the process is about 20 cents per pound of methanol product produced. There's clearly a deficit here in our operation, making it impossible to turn a profit, let alone be able to pay back whatever capital costs that we incur during construction. From our economic analysis, we determined our after-tax rate of return to be below negative 30%. In addition, the net present worth after 3 years of construction and 15 years of operation comes to be approximately negative $573 million. Of course, along with these, the cash flow is also in the red. Here, you can see how the net present worth of the process continues to decrease over its lifespan. It was determined for the process to reach the economic goal of the company, a target 15% of after-tax rate of return, that the net back for the methanol would be approximately 39.4 cents per pound. This is an increase of about 315% of the current value of methanol. We performed several alternative studies and sensitivity analyses on this process. However, none of these options were identified to increase the profitability of the process significantly enough to make the process economical. Therefore, it is not recommended to develop the process further, since no profits are predicted to be made with current nor predicted future markets.
For our process to be viable, it needed to meet several process, safety, and environmental specifications. The first one I want to discuss is the disposal of waste. Our process followed a cradle-to-grave technique, meaning that everything that came into the process needed to leave in a very specific way. We used several wastewater treatment techniques, as well as recycling other waste streams into our direct fired heater to lower utility costs for that process unit. I also want to talk to you about regulation of conditions in process units. As we've all mentioned, there were several process units where the temperatures or pressures were very high. To make this safer for our plant, we installed several process control units that could be tripped in the case of emergency situations where the pressure reached unsafe heights. An example of our process control units are the ones attached to the adsorption units. As we've mentioned, we actually had 2 adsorption units in series. So a process control unit on the end of the adsorption column on the effluent stream would actually monitor the concentration of the mercury or hydrogen sulfide in that stream. So when it reached an unsafe level, we could actually trip that system to turn a valve before the column to move over to the other adsorption column, which would be fresh and ready to adsorb that contaminant. We also had pressure relief systems installed in our process, again to deal with the safety of high pressure systems. As Emily mentioned, our plant is not economically feasible as we have designed it. In order to meet an economic situation where Nitline Chemical would actually want to design this plant, we have several significant changes that would need to happen. The first of which that I want to discuss with you is the sulfur removal technology. As we mentioned, it was very expensive, and we would need to take a completely different approach in order to find an economically feasible technique to remove the hydrogen sulfide. Again, the conditions in the steam reformer and the methanol synthesis reactor were very far from ambient conditions. With the high temperatures and high pressures, a lot of money would need to go into building and maintaining these process units. If we could change these to more moderate conditions, it would be possible to actually be able to afford these units. On this same note, if we could also use less refrigerant in our process, we could save a lot of money because the propane refrigerant is very expensive. This ties into the same moderate conditions in our process. So if we could find a way to still meet the methanol production rate at lower conditions or more moderate conditions, this would be much better for our economics. Thank you for your time.